All right, for slide 20, we have Haley's comment. It's giving us two distances, one close and one far, and then it tells us the velocity at the closer distance. What it's asking us to find is what is the speed when it's further away. It tells us that angular momentum is conserved, so we know that its angular momentum when it's close is equal to the angular momentum when it is far. Now our equation for angular momentum, if we expand that, we know that angular momentum is equal to I times omega. So that's its moment of inertia multiplied by its angular velocity. And we're going to have our two conditions. So there's when it's close and when it's far. We'll expand that a little bit further because we know the equation for I, for its moment of inertia, is just mr squared since it's a point mass. And our equation for omega, for the angular speed, is its velocity over the radius. So we're going to go ahead and substitute that in for both sides. And it's going to get a little bit messy. But it's a straightforward substitution. From here, we're going to go ahead and try to clean and clear some stuff out so we can see that mass and mass on both sides. That'll reduce out. We can see that RC squared over RC, the square, and one of those will cancel out. Same thing on the right-hand side for when it's RF. And so that simplifies a lot. And what's left over is much more straightforward. Ultimately, what we're trying to find is VF, the velocity when it's far. So we'll go ahead and manipulate that around. And our final equation will just be this. It's a ratio of the radius when it's close over the radius when it's far multiplied by the velocity when it's close. We know as things get further away, they're going to slow down. So we understand that our final velocity when it's far is going to be smaller than its velocity when it was close.